Hello everyone. In today's lecture, in continuation of the architecture of NVIC and in exceptions, we are going to discuss about the NVIC and system control block. So what is NVIC? So NVIC is a special feature of ARM Cortex-M0. It is nested vector interrupt controller. When we discuss about exceptions, we have discussed around 47 exceptions. We have around 32 normal IRQ exceptions. And a few special exceptions were also there, like NMI, reset, system tick lock, and so on. These much of exceptions can be handled by ARM Cortex M0 without any special feature, right? So let us see how it was being handled. This special feature is known as nested vector interrupt controller. That is, since it can handle more number of interrupts. See, once when one interrupt enter inside before completion of that first interrupt, second interrupt can also enter inside, third can also enter inside. And let us see how, if multiple exceptions enters inside or if multiple interrupts enters inside, how the processor is going to um, manage this interrupts. So this is the basic feature of ARM Cortex M0, and the the feature which improves the system efficiency too. This is the diagram. Already we have discussed this with our when we explain about architecture. Interrupt 1 has not been over. Before that, interrupt 2 has also entered inside the processor. So these registers, they are memory mapped with the address located with the system control spaces. The below are the NVIC features that makes ARM Cortex processor to respond better, to reduce the program size or the code size, and also in managing the exceptions in the NVIC hardware. The special features of flexible interrupt management, nested interrupt support, vectored exception entry, interrupt masking. These are the special features. Let us see flexible interrupt management. In Cortex M0 processor, each external interrupt can be enabled or disabled and can have its pending status set or clear by software. It can also accept exception request at signal level. This allows the interrupt controller to be used with any interrupt source. Nested interrupt support. In Cortex M0 processor, each exception has a priority level. The priority level can be fixed or programmable. When the exception occurs, such as an external interrupt, the NVIC will compare the priority of this exception to the current level. If the new exception has a highest priority, the current running task will be suspended. Some of the registers will be stored onto the stack memory, and the processor will start executing the exception handler of the new exception. This process is called preemption. When the higher priority exception handler is completed, it is terminated with an exception return operation, and the processor automatically restores the registers from the stack and resumes the task that was running previously. This mechanism allows nesting of exception servers without any software overhead. Next is vectored exception entry. When the exception occurs, the processor will need to locate the starting point of the corresponding exception handler. The Cortex M0 automatically locates the starting point of the exception handler from the vector table in the memory. As a result, the delay from the start of the exception to the execution of the exception handler is reduced. Next feature is interrupt masking. The NVIC in the Cortex M0 processor provides an interrupt masking feature via the try-mask special register. This can disable all exceptions except hard fault and NMI. This masking is useful for operations that should not be interrupted, such as time critical control task or real time multimedia codecs. Then we have the system control block. Apart from NVIC, the system control space also contain a number of other registers for system management. This is called system control block. Although it is currently, then we have the debug system also in the system control block. Although it is currently the smallest processor in the ARM processor family, the Cortex-M0 processor supports various debug features. The processor core provides halt mode debug, stepping, and register accessors, and additional debug blocks provide debug features like the breakpoint unit, BPU, and data watch point units. The BPU supports up to 4 hardware breakpoints, and the DWT supports up to 2 watch points. Then we have the system control block. To allow a debugger to control the aforementioned debug components and carry out debug operations, ARM Cortex-M0 processor provides a debug interface unit. This is through a JTAG and a serial wire debug protocol. And these are the control units, and here we have how it was been interconnected. Thank you.